Hi guys, how's it going? Today we'll be going over limits. So what does it mean? What does a limit mean? The limit definition of a derivative. And we will finally also go over limits at infinity if we if have time. So let's get started. Okay, so the first point that we want to look at. So first, before we jump into the problem, what is a limit? So a limit is how close we get to a certain point. Let's say we have the graph x equals y right here, and we want to find the limit as x approaches 1. So as we get super close to x approaches 1, what is the number that we get on the function? And so in this case, we can literally just plug in 1 to the equation, and we just have 1. But in a lot of functions, such as in this case, it won't be as straightforward. So this is what we want to cover with limits. Another thing to really point out with limits is that limits really lays a foreground for calculus. Like when you take a derivative, it's basically a bunch of continuous limits. So it's a pretty crucial moving forward into calculus. But let's get started. So when we look at this graph right here, we see a lot of weird points. We see a cusp here. We see something weird here. Another removable discontinuity. So we got our work cut out for us. So when we look at what is the limit as x approaches 3, well, we look at the limit as x approaches 3 from the left, and x approaches 3, from the right. So for a limit to exist at a certain point, the limit as x approaches any number, let's call it a, from the right must equal limit from x approaches a from the left. If you want to have a limit, this is crucial to have. So let's jump back into the problem here. We have limit as x approaches 3 from the left. We have, if we go from the left, x approaches 3, a goes to 2. And limit as x approaches 3 from the right, so we go this way, and we have 1. And so from here, we see that limit as x approaches 3 from the left is not equal to the limit as x approaches 3 from the right. Therefore, the limit as x approaches 3 does not exist. Okay. Now moving on to our next point that's very, let's say, sketchy. So here we have a removable discontinuity basically with what is the limit as x approaches 6? What is it? Well, let's go through the process again. Limit as x approaches 6 from the left, and limit as x approaches 6 from the right. From the left, we have x approaches 6, so we have 2 right here in line with 2. And from the right, as we go down, we have x is equal to 2. So from here, we can in fact say that the limit as x approaches 6 is equal to 2. Now, the reason why it's important to look at this rather than just plug in the number is because if we had just looked at f of 6, it would have been 3. So this is a case where the limit of x approaches a is not equal to f of a. This can hold true. Let's say if we were looking at the limit as x approaches 4, limit from the right and from the left both approach 0, and f of 4 is 0. So therefore, that would be an instance where this would not be. This is true, but this is not always true. That's a very important thing to note. Now moving on to the limit definition of a derivative. So this is how we first get introduced to derivatives, and it's very important to know why we look at it this way and why is it important. So we have a function, let's say f of x, and you don't know what the derivative is, but we don't know how to take a derivative, let's say. We haven't learned power rule or anything like that, take a derivative. So what we say is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, sometimes they just give you the equation, but really, this, if you look at it closely, is just a point on the graph. So if we were to look at this graphically, right here, we have, say this is x, and this is x plus h. We also know this is the rise over run. So f of x plus h right here, and then this is f of x. So if you look at rise over run, we'll have f of x plus h minus f of x all over x plus h minus x. So the minus x and the x should cancel out, and this is what we're left with. So that's how we get this part of the equation. But why would we take a limit as h approaches 0? Well, we want to know, as we get these 2 points infinitely close to each other, what is going to be the slope there? And so, at that, as we bring these 2 points super close together, what it will be our slope. And so that is what a derivative is, a slope at a very small point. And so, a lot of times they can give you a function, you plug in your function, and a lot of times you do a lot of fancy algebra to cancel things out. Another thing to note is that there will be another function, another equation that you will be introduced to with h in terms of a, but I won't be covering that in this video because it's very, very similar to this concept right here. So next and finally, let's hop into limits at infinity. So when we look at f of x is equal to infinity or negative infinity, it's important to look at it, what does it mean on a graph? Like, what can you relate it to? And so if, let's say, this is going to be a wildly inaccurate graph, but let's say that this is f of x is equal to something like that, and you have an asymptote right here. As x gets infinitely big, this line will approach the asymptote. And so really a question that we could be asking is limit as x approaches infinity right here. As it goes off to infinity, what is it going to approach? So in other words, what is this asymptote? Okay. So how are we going to do this? So first, we'll start off with negative infinity. Now it's important to note that sometimes, not always, negative infinity and infinity will both come out to the same, but not always. And so let's test out as x approaches negative infinity. Well, first I like to factor things out, so we're going to rewrite this. No, that's not important to factor out. And we'll factor out x from the bottom here. So, for very obvious reasons, we can't just plug in negative infinity because we'll have negative infinity over negative infinity, basically. Or infinity over negative infinity. Either way, it won't work. So what we can do is we can multiply this whole thing by 1. But, a very special one, I would say. Be 1 over x squared. So, I'll explain a little bit later why I chose this. And this step is really not useful, but the reason why I chose to multiply by 1 over x squared will really show later on. I chose the highest degree on the top and the bottom. If this was x cubed, I would have just chosen 1 over x cubed. And then from here, what I can do is multiply it through, right? So this should be to both sides. We got 8 over x squared minus 4, because it's x squared over x squared, just cancels out, over, and then same thing on the bottom, 9 minus 5 over x, right? And so as x gets really, really big, these two terms are just going to go to 0, right? Because 5 over infinity is going to be 0, because you're having an infinitesimally large number in the denominator. Same thing with 8 over x squared. And so we can say that's going to be negative 4 over 9. Now, if we looked at our thought process throughout this whole thing, we can see that infinity and negative infinity won't change our result in the end. So we can deduce. If I was doing this on a test, I would really show and really take the limit at x if e approaches infinity as well. But we can deduce that limit as x approaches infinity of f of x will also approach negative 4/9. I hope this made sense, and I hope it was really useful. Limits is really starts off what calculus is, because when you start looking at what a derivative is, the first thing we look at will be that limit definition of the derivative. I hope you found this video useful. Please let us know in the comments below what you would like us to cover next and what would be useful moving forward. Thanks for watching.